Hi everyone, this is Mr. Lee. In this video, we are going to go over Gauss's law. More specifically, we are going to go to the intro ideas of Gauss's law. There will be 3 videos after this that goes into the different shapes that we will be analyzing for Gauss's law. So let's begin. Gauss's law, I'm just going to abbreviate that from now on as GL, relates the electric flux through a Gaussian surface to the Q enclosed. So as a reminder, electric flux is the symbol phi with a subscript of E, and this is equal to the electric field dot product of the area vector, okay? And all of these are vectors, which is just the absolute value of E times A cosine of whatever the angle is. Okay, so we're going to analyze this definition in a little bit more specifics with a couple more examples. So the important thing is, and you'll hear me say this throughout the video and in class, okay, you can only use Gauss's law when there is symmetry. It is a very powerful tool, and our math becomes like so much easier by using Gauss's law. But the only limitation is you can't use Gauss's law for any kinds of problems, only when symmetry is applied. So up until now, we did electric fields of different charge distributions. So for those scenarios, we cannot use Gauss's law because this idea of symmetry will not apply. And I'll show you exactly what that means in a little bit. Okay, so let's take a look at this example here. We have a positive charge here, and in red I drew the electric field, and you can see these tiny little rectangles that I put all throughout the electric charge. Those are my areas. Okay, and so here's the stipulation for the situation. I drew each one of those area windows at a specific distance r away from the charge. Okay, and because this is just a regular charge, the E field strength at each one of those windows is equal to each other. And so what this shows us here is that the flux at each one of those windows will be identical to each other because the E field is the same for each one of those points and the area vector is the same for each one of those points. Okay, now when we create an infinite amount of those windows, what we're creating here is a sphere. So this is not like a real sphere, it's an imaginary sphere that goes around the charge, and this imaginary sphere is what we call the Gaussian surface. So the Gaussian surface is a powerful tool that we can use to analyze, hey, if we were to enclose this charge with all of these tiny little windows, okay, at a singular point r away, okay, what is the E field at that point? So it helps us determine E at a point r away if we know the charge that is there. All right, and so the idea of symmetry is important because this E field at this point r has to be the same E field at this point r. And we can say that at any of these infinite amount of points around that makes this sphere will always be the same E field due to symmetry. Okay, and there's actually 3 different Gaussian surfaces that we will create in our class. The sphere is just one of them. Okay, now once again I'm pointing out this key idea here. It only works due to symmetry, and over here I have an example as to why. So if we have the same charge, but instead we drew the Gaussian surface that looks like slightly askew. So I'm going to redraw it here so that you can see me draw it. All right, so it's a little oblong there. So the question is, why won't this Gaussian surface work? And the idea is we need to make sure that the E field is the same no matter where we are looking around the Gaussian surface. But if our Gaussian surface is enclosed in something that is not like symmetrical, like what we have here, we have different areas of the Gaussian surface that sees a stronger E field versus another. Okay, so one of the techniques that we need to be able to do while doing a practice problem is actually drawing the Gaussian surface. It's equivalent to us having the ability to draw a free body diagram, right? So drawing a free body diagram correctly leads to solving the problem correctly. Drawing a correct Gaussian surface leads to solving the problem correctly. Okay? So symmetry. Now, let's go into the actual formula itself. There's two versions of this formula. There's the algebraic formula, which you will see up here, and the calculus formula down here. We're going to go with the algebra one first. So Gauss's law says that if you are enclosing a charge, okay, if you are enclosing a charge, and that charge is producing an E field, and that E field is going through a area, we have flux. Okay, and this symbol down here, if you remember, this is epsilon naught, and epsilon naught is the permittivity constant, which is, what was it, 8.85 e to the negative 12 c squared over Newton meter squared. And if you remember, this is the idea that E fields can exist in a vacuum. Okay, so in order for an E field to exist, we must have a charge, and if we enclose that charge, we get this idea called a flux. Okay, so it's a weird way of describing a scenario. So if you have a charge and you enclose it in a Gaussian surface, we know that flux exists, right? So flux. And we know that the E field exists, so E field is good, and therefore, like that, I mean, that is Gauss's law. There's no other way of putting it. Now, the calculus version is a little bit more complicated. So the calculus version, what we're doing is we have a brand new symbol. It kind of looks like the integral symbol, but there's a little circle inside of it. In some textbooks, you might see a double integral symbol with a circle through it. But essentially what that is it's called a closed integral. Okay, and for us, the closed integral has a very specific meaning. So oftentimes you'll hear me call it the closed surface integral, and the closed surface integral, what it equates to is when you're creating your Gaussian surface, okay, if you find the surface area of whatever shape you're creating, that is equal to this. That is equal to the surface integral dA. So if you have a sphere, this would just equate to the formula for the surface area of a sphere, right? The same goes for a cylinder, and the same goes for a, let's say, a rectangular plane. So if you have a Gaussian surface and you're looking at a rectangular plane, right, this would just be like base times height, all right? So it's just the area of whatever your Gaussian surface is. So GS is the shape that you yourself will need to draw around the charge. And once again, that is a technique that you will do when you are solving the problem. Sometimes the problem gives you a Gaussian surface to work off of, but you are required to look at a situation and be like, all right, in order to make this symmetrical, I have to create this Gaussian surface. All right. Now, the idea here is, due to symmetry, we can only create the 3 Gaussian surface that we will work on, and I do these in our 3 separate videos. So we have the Gaussian sphere, we have a Gaussian plane, and we have a Gaussian cylinder, and each one of those has a specific closed integral area formula that we can use. All right, so that's the intro. In the next video, I'll go over the Gaussian sphere. I'll see you next time. Bye-bye.